Hello, it's so loud. I'm Jane. I am from TU Delft, and I'm working with Ferry. He's here now, and Bas, he couldn't join us. Oops, that's fine. Okay. As a general topic today, the shockwave boundary layer interactions. I'm going to quickly remind you again why we are interested, because we have very wide range of high-speed applications, and we all know that when the flow is exceeding entering a speed regime, we start seeing some shock formations, and this is happening in different kind of applications. And to understand this effect of this shock waves, we need to actually look a little bit close to the surface flow. Here, I sketched type of shockwave boundary layer interaction that I will be focused today in my talk, which is an oblique type of interactions. There is an incident shock coming and impinging to the boundary layer, and it is so strong that it is actually causing the separation of the boundary layer, that we can see the separation shock and the reversed flow occurrence in the boundary layer. And this flow reversal, this separation of the boundary layer is actually also inducing an unsteady loads to the structure. So what we want to do is we want to avoid all these consequences. So we want to control. And today I will talk about a specific type of control device, which is shock control bumps. And the main idea, as Timothy also said, is kind of removing that separation bubble and filling it with something solid like a wall. I did some experimental campaign, and I will mention you about that, and I will try to explain how did we came up with a more universal design, or the first step of that design, let's say, and then I will show some results and mention about the upcoming work about that. These shock control bumps are not something new, actually. They have been the topic of the discussion quite long time. And here we are actually seeing a three-dimensional shock control bump used for controlling a normal shock wave boundary layer interaction. A normal shock is a strong shock that we do not like generally in the flows. And this bump is actually, what it's doing is changing this normal shock wave structure into the oblique, like inducing an oblique shock in just the start of the bump. And this way it aims to kind of lessen the shock losses and having this kind of benefit in the flow. This different research groups also, when they were looking at the three-dimensional bump shapes, they also find out this kind of shape is actually having another benefits in the flow. They find out that it is actually inducing in the downstream flow some streamwise vortex pairs. Why this could be an interest? Because this vortex pairs can energize the boundary layer, and it could make it more resistant to any downstream separation. So by looking all of this type of control is quite promising for the normal boundary layer interactions. But how about the oblique type of interactions? So what the idea is, yes, the separation bubble in theory could be filled by that kind of structure, but mostly this more conventional bump is consisting kind of a ramp shape and then the tail part. So my idea is this device is going to change the interaction. For sure, it's going to modify. So how can we understand that it's going to modify in such a way that it will act on this main interaction strength? So if we can manage to introduce some compression waves or some weak leading edge shock, that will modify the upstream conditions of the main interaction. So if we can remove the separation from the flow, as a consequence, we can also reduce the unsteadiness and unsteady loads on the structure. So this is quite beneficial. And what I looked generally, I looked of this shape and its effect, how does it modify the interaction of the type of interaction, and how can we remove the separation, and as a consequence of that, how can we reduce or remove, hopefully, the low frequency unsteadiness. And today I will focus on only the investigation on the geometry side of it. And when I'm doing this investigation on the geometry, I also will focus only on this angle on the ramp part. So here you can see a conventional shape bump. As I briefly said, it is including one ramp part, and there is a small crest, and then the tail part. And the bump height is, I will tell that bump height, and I will be referring to the maximum height that it is reaching on the crest. And when I'm in this investigation, we kept the bump height constant and all the tail part parameters constant, and we just focused on the ramp part and how does it change the effect. And if we keep the height constant and if we change the angle, naturally we are also changing the length of the ramp part. So what I tried to explain before by modifying the interaction is actually here maybe a little bit more could be seen. When we introduce the bump, we are actually changing the wall conditions, as someone mentioned, and we are introducing here as some kind of compression type of interaction. And then our main incident shock, main interaction is happening actually on the downstream of that compression corner. So by deflecting this flow just prior to the main separation, we are hoping to act on the strength of this main interaction. But for when we are designing the geometry, of course, we want to get rid of the separation. We don't want to introduce more separation. So we needed to be careful that this ramp angle is in the range of that flow is not expected to separate. And on the design, we came up with the idea of, okay, we can take the well-established approach, and then we can take that as a reference for us to understand what could be a reference ramp angle for us. So when we are designing, we looked at just a natural, uncontrolled interaction. And from my old experiments, I derived this streamlines kind of, and try to understand the flow deflection after the separation shock foot. And then what we try to do is what we try to understand with that kind of flow deflection, how can we optimize introducing another oblique shock to have the optimal total pressure recovery over the overall interaction. And this gave us a result of around 4.6 degrees of ramp angle for a baseline case. But we also tried different angles to understand how the effect is varying. Keeping this 4.6 degrees as a baseline case, we also tried a little bit lower and higher degrees. For all these cases, the height is kept constant, and from the literature, we know that it is mostly preferred that the height is taken in order of the boundary layer thickness. So for the simplicity of the comparison, I stick with that. And here, just I'm presenting two different cases with some average Schlieren images that you could see on the vertical line, and then respective oil flow visualizations for no bump and bump case. As here you can see, we have a quite large separation, and it is very clear the separation line and the reattachment line in this case, where this dark line is the incident shock, and here we can see the separated shock. When we move to the bump case, we can see it's clearly different, especially the oil flow topology. When we look at the side parts where there are no control, we can actually see some kind of resemblance with the uncontrolled case. There are clear separation, but on top of the bump, it is getting a little bit more complicated to understand that we don't see clear line of separation and reattachment. So it tells us something, but not so clear. Also, what we realize that the mentioned vortex generation effects were also quite present in the cases with the bump in the oil flow. And this is what is like what is thought also in the previous research is suggesting is that these vortices are originated most probably is over this focal points, and then it's traveling downstream. Yeah, but this is quite three-dimensional and highly complex topology. To a little bit more understand, we just went through the PIV measurements, and I just used two cameras in the planar configuration to focus on the interaction and to focus on the both upstream interaction and again interaction and downstream part. So when we merge these two field of view with this overlap, we are arriving this full overall field of view. So the aim was like understanding really the effect on the flow separation, and hopefully maybe getting some movements. This is not a high-speed PIV, but still like by detecting the flow, we could maybe have an idea about how the shock is moving. Also looking at the downstream effects. And here we can see a wall normal component of three different cases. The first one being uncontrolled no bump case. The flow is shown by the streamlines. And here we can see that there is an area of the streamlines are directly like following the separation bubbles shape. And when we follow these lines, it's actually in overall, if we look, it's not maybe that's different, but I went and checked the deflection angles. It's like then we cannot see actually the differences in little subtle differences in the flow. And we can, for example, see for the lower angle cases, 4 degrees and 4.6 and 5.4 degrees, we can clearly see the two-step flow deflection. But after that point, it's getting a little bit trickier. And when we look at the streamwise component of the mean velocity, what we see in the average flow fields, we see some flow separation in the no bump case. We do not actually see any of the bump cases. And we do see some slight differences in the, when we follow the shock both of the incident and reflected shock lines. We do see some differences, decrease in the interaction length. But we cannot directly jump into conclusion with this. So we need to check how the instantaneously flow is changing. When I check the instantaneous flow, I have seen actually separation occurrences are happening for all the cases. So what did I do? This is a very basic video, but I wanted to show just because of like how well we are following the shock. This is a no-bump case, and we developed a shock detection algorithm, let's say, to follow both of the steady incident shock and the reflected shock. And this gave us like, in the end, when I look at where the reflected shock is impinging on the wall, I could understand maybe that how much it is oscillating and unsteady behavior. It has unsteady behavior. So the no bump case is, as a reference, gave us around 0.6 delta, where delta was around 5 millimeters. As a reminder, this is, I'm sorry that this is millimeter, should not be there. And since we tracked both of the shocks, we could also derive the interaction length. And the mean interaction in the case of no bump was around 5 delta. And the change of this interaction length was around 0.4 delta. But compared with the bump cases, actually, we could see decrease in these values. The optimal result was given by this 4.6 degrees ramp angle, which we chose as a baseline. And it's almost gives half of the standard deviation in the impingement point for the reflected shock. And also we could see the reduction in the interaction length, average interaction length, and also the standard deviation of the change in the interaction length. But we saw some interesting result as well. When we moved to the 6 degree, approximately 6 degree ramp angle, even though we could see a slight reduction in the average interaction length, actually we did see quite an increase, not quite, maybe it was around the baseline case, around the no control case, the standard deviation of the impingement location of the reflected shock. I am not sure at the moment what does this mean. It could be related because of that when we change the angle and keep the height constant, as I said, we are changing this ramp part of the bump. So it could be something to do with that, because we are, when we introduce the compression corner directly in the interaction region, it could make things a little bit complicated. So this is something to look at for me. And to understand better the fluctuations in the flow, we also looked at the turbulent intensity. And in the no bump case, clearly we can see here, we do see also slight faded shock waves, and the shear layer is going, and then the highest turbulent intensity values are seen in this region. When we move to the bump cases, I plotted only the geometry has been chosen as the reference baseline bump geometry. There are some things in here, but it could be because of the outliers in the measurements. But the most interestingly, in here, we do see a different evolvement in the turbulence intensity. And we do see only the shear layer response. And we can say that it's actually modified quite much. also when we look at that, we can slightly see the leading edge effect, and then this part is for the interactions kind of reduced. But when we look at the 6-degree case, there is this part, which could be, again, some effects of the bump design. And we do also see that there is no clear separation shock food, but it's more like their waves kind of. So this is definitely an interesting case to look at for understanding the effects of these parameters. And to understand how the separation is removed, or if it's really removed, I also checked the separation probability, which the criteria for the separation probability is taken as the flow reversal. So we went and checked all the instantaneous PIV images and then computed the probability of the occurrence at that point for the flow reversal. And it gave as a maximum separation probability in the no bump case, as being 60% of the time is flow is separated. And when we move to the bump cases, it's reduced this maximum probability very much. In the best case was this one, and I don't know if you can see above this slice of bump, like there is a little flow reversal probability. It's around 15% of the time the flow is, it says that reverse in that area. So it is very much reduced and confined in a small area. And then from 60% of the time to 15% of the time is we could reduce the reverse flow probability. And when we look at 6-degree case, actually we do see this time is only we could reduce it to a 30% of the time the flow reversal probability. And in here we can also see that where we saw the turbulence intensity was higher in that region, we can also see the flow reversal in the different instances of the PIV images. Now, what to do is I will add up to this study to how the flow is behaving downstream of the interaction and the downstream of the bump. And also I have some data from the span-wise velocity distribution to understand better that how the velocity is developing downstream of the interaction. And I think the most exciting part is really understanding how the bump is changing the interaction physics. So for that purpose, I'm working on investigation on the two-dimensional bump design to better understand the effects of this parameters, and then hoping to understand the main driving mechanism behind the working principle of the bump, and also coming up maybe hopefully with a model for a parameter, and to also better understand the effect on the unsteadiness. I hope to do some measurements also with the high-speed time resolved PIV. And that's it.